Hey everybody, welcome back to trigonometry. Today we're in section 6.1 and we're going to be talking about inverse circular functions. In this section we'll do a brief review of inverse functions in general, and then we will talk about the inverse function for each individual circular function, and we'll practice calculating a couple of values at the end. Here we go. So you might remember from algebra that the definition of a function is that each input can only produce one output, and the inverse of a function just reverses the input and the output so that the function runs backwards. So imagine I have a function here, and you can kind of think of it as a little machine. And let's imagine that we feed a 1 into this function and we get out a 5. Now you don't know how the function is doing this, but you know that every time you put in a 1, you get out a 5. And let's imagine that every time you put in a 3, you get out an 11. And every time you put in a -2, you get out a -4. And that's how that function works. So that means that the inverse function for f would have to work like this. If we feed the inverse function a 5, it has to put out a 1. If we feed it an 11, it has to put out a 3. And if we feed it a -4, it has to put out a -2. So you see that whatever the function does, the inverse function just runs backwards from that. Now if our function is f of x, then the inverse function is written like this, and it looks like we have a -1 exponent here. But don't confuse the -1 in f inverse of x with a negative exponent. This symbol does not represent 1 over f of x. Instead, it represents the inverse function of f. Okay, now let's start thinking about inverse circular functions, and we'll start with the inverse sine function. So think about the function that we already know, y equals sine of x. This is a function because every angle only has one sine value. So each angle that we input can only produce one output. But if we reverse the input and the output so that we have an inverse, then we have sine inverse of x equals y. And in this case, the input is a sine value and the output is an angle. Now this is an inverse because you can see that these two are swapped from how they were before. But on its own, this is not an inverse function. So why not? Because an inverse can only be called an inverse function as long as each input corresponds with exactly one output. Remember, the definition of a function is that each input corresponds to exactly one output, and that holds true for inverse functions as well. But we know that each sine value matches more than one angle. For example, the sine of 30 degrees is 1/2, but the sine of 150 degrees is also 1/2. And any angle that is coterminal with either of these also has a sine value of 1/2. So for example, the sine of 390 degrees is 1/2, and the sine of 510 degrees is 1/2, and we could go on and on calculating angles that are coterminal with 30 and 150, and we could just collect an infinite supply of angles that have 1/2 as their sine value. So if we think about what that does to our function machine, you know, as long as we're working with the sine function, we're fine. If we put in a 30-degree angle, we get out a sine value of 1/2. That's the only sine value we'll ever get out if we put in 30 degrees. So this input matches only one output. And the same thing goes for 150 degrees. Every time we put in 150, we get out 1/2. So this input produces only one output. And the same thing goes for 390 degrees. If we put in 390 degrees, we get out 1/2. So everything's fine as long as we're talking about the sine function. But now think about the sine inverse. If we put 1/2 into our sine inverse machine, what will we get as an output? Do you see the problem? The problem is that when we reverse the input and the output to form the inverse of y equals sine of x, we see that each sine value that we input will match an infinite number of angles that should be outputs, and therefore each input matches more than one output, and that disqualifies this from being a function. So without some additional specifications, y equals sine inverse of x cannot be considered a function. So to solve this problem, mathematicians had to agree to limit the range of y equals sine inverse of x. In other words, we limit the angles that can be produced as outputs, so each sine value will match only one angle in this limited range. So think about this. If we limit the angles that sine inverse can give us as outputs to just quadrant 1 and quadrant 4, then that will do the trick, because any negative sine value that we plug into the sine inverse function would only give us one quadrant 4 angle, and any positive sine value that we plug into the inverse sine function would only give us one quadrant 1 angle. And these two quadrants are really all we need, because remember, sine values can only go from -1 to +1. And here, between these two quadrants, we have every possible sine value represented. Remember, the sine values are the y-coordinates of each point on the unit circle. And so if this is the unit circle, or half of it, then the y-coordinates of the points on this unit circle are going to go from -1 to 0 and then up to +1. So every possible sine value is represented here exactly one time. Okay, so in order to make sine inverse of x into a function, we limit the range so that the only outputs are in the interval from -π/2 to +π/2. Or if you wanted to think in degrees, you could think from -90 degrees to +90 degrees. So this works because the range of angles from -π/2 to +π/2 has sine values that go from -1 to +1, and each sine value is represented exactly once, so none of the values repeat. And now each sine value or input matches exactly one angle or output, and that makes sine inverse of x into a function. So now, whenever you see y equals sine inverse of x or y equals arc sine x, you can think of that as y is the number or angle in the interval from -π/2 to +π/2 whose sine value is x, whatever number you have here. Now the domain of a function, you'll remember, is the set of all values that can be plugged into that function. And for sine inverse, that would be any possible sine value. And we know that sine values have to be between -1 and +1. So the domain for y equals sine inverse of x is -1 to +1. And again, that's the set of possible sine values that can be inputs. Then the range of y equals sine inverse of x is the angles that can come out of this function. And we just said that the angles we can get out are the angles from -π/2 to +π/2. So for y equals sine inverse of x, again, we can plug in any sine value between -1 and +1, and we can get out any angle between -π/2 and +π/2. So here's example 1, and let's just practice working with the sine inverse function a little bit. So in part A, it says y equals arc sine of 1/2. Now you remember that the arc is just the older notation for the inverse function. So arc sine and sine inverse mean exactly the same thing. So right here we are looking for an angle between -π/2 and +π/2 whose sine value is 1/2. Now because this sine value is positive, we know that the angle is going to be in quadrant 1. And this happens to be one of our memorized sine values. So we know that this sine value of 1/2 matches a reference angle of 30 degrees, and in radians that would be pi over 6. So y equals pi over 6 radians. In part B, we have y equals sine inverse of negative square root of 3 over 2. Okay, so again, we're looking for an angle between negative pi over 2 and positive pi over 2, whose sine value is negative square root of 3 over 2. Now, since this sine value is negative, it must be indicating a quadrant 4 angle. So let's draw a quadrant 4 angle. Now remember, it will be a negative angle because our output has to be between negative pi over 2 and positive pi over 2. So we're not going to be going around in the positive direction. That would give us an angle bigger than 3 pi over 2. And our results for sine inverse always have to be between negative pi over 2 and positive pi over 2. Okay, so here is the angle we're trying to think of. And again, square root of 3 over 2 is one of our memorized sine values. This matches a reference angle of 60 degrees. So what we have here is an angle of negative 60 degrees, or in radians, negative pi over 3. Now let's look at part C. So here we have y equals sine inverse of negative 1. Now you know that sine values of negative 1, 0, or positive 1 are all going to indicate quadrantal angles. So we know that for the angle we're trying to find, the terminal side will have to go through a point where the y value is negative 1. And there's only one place on the coordinate system where that can happen, and that is if the terminal side points straight down. Okay, so again, this has to be a negative angle because we're limited to angles between negative pi over 2 and positive pi over 2. And we know that this is negative 90, or in radians, negative pi over 2. And then for part D, it says y equals sine inverse of negative 2. So in this case, we would be looking for an angle whose sine is negative 2. But we know that there is no such angle because sine values can only be between negative 1 and positive 1. It's not possible for an angle to have a sine value that is negative 2. And so this angle does not exist. Now here is something for us to be careful about. We always want to be sure when we're working with inverse functions that the answer we're giving is in the range of the particular inverse function we're considering. For example, the sine of 210 degrees is negative 1/2, but as you know, the inverse sine of negative 1/2 can't be 210 degrees because 210 degrees is not in the allowed range. Sine inverse is always supposed to give an angle between negative 90 degrees and positive 90 degrees, or in radians, negative pi over 2 to positive pi over 2. So that's just something to be careful about. Now let's move on and talk about the inverse cosine function. This function has a problem similar to what we saw with the inverse sine function. Every cosine value matches an infinite number of angles. So to solve this problem and make inverse cosine a function, we can do a similar thing to what we did with the inverse sine function, but we can't use the same range. Negative pi over 2 to positive pi over 2 will not work here, because notice that cosine is positive in both quadrant 1 and quadrant 4. Therefore, every positive cosine value matches up with two different angles, and you know we can't have that. And to make things worse, our negative cosine values don't match up with any of these angles. So we need to choose a different range. We need to choose two quadrants where all the cosine values from negative 1 to positive 1 are represented. And the most natural choice for that is 0 to pi radians. So that would be quadrant 1 and quadrant 2. So we can think of y equals cosine inverse of x, or y equals arc cosine of x, as saying y is the number or angle in the interval from 0 to pi radians whose cosine is x. Again, the input for this function is the cosine value, And the output for this function is an angle between 0 and pi radians. So the domain or input for cosine inverse of x is -1 to +1. And the range or output of cosine inverse is going to be any angle in the interval from 0 to pi radians. So let's practice with that here in example 2. It says find y in each equation. And part A says y equals arc cosine of 1. So we're looking for an angle between 0 and pi radians whose cosine is 1. Now, again, this is going to be a quadrantal angle, and so we want to think of the angle whose terminal side goes through the point 1, 0, and that would, of course, be the angle 0 radians. For part B, we have y equals cosine inverse of -√2/2. Okay, remember, cosine inverse has to give us an angle in either quadrant 1 or quadrant 2. Because this is a negative cosine value, we know that we're looking for a quadrant 2 angle. And because the cosine value that's being plugged in here is -√2/2, we know that the reference angle here will be 45 degrees. That means that the standard position angle is 135 degrees, or in radians we would say 3 pi over 4 radians. And remember that when you're working with a reference angle of 45 degrees, you can count half quadrants instead of converting. So you could take 135 degrees and convert it to radians, but you also could say that this angle covers 1, 2, 3 half quadrants, so it's 3 pi over 4. Now let's go on and talk about the inverse tangent function. Since tangent is positive in quadrant 1 and negative in quadrant 4, tangent inverse can use the same quadrants as sine inverse. So we're back to a range of -pi/2 to +pi/2. But we have to remember that tangent of pi/2 is undefined, and tangent of -pi/2 is also undefined. So those two values have to be excluded from the range. Now, you remember that any number can be a tangent value, so the domain of tangent inverse is going to be -∞ to +∞, and the range of tangent inverse is any angle between -pi/2 and +pi/2, but excluding those two angles. So technically, we should write the range as parentheses, -pi/2 to +pi/2, close parentheses. Now for us, the brackets or parentheses on the range of our inverse functions will not be a big deal. It's much more important that you know which quadrants to go to. So as long as you know that sine inverse and tangent inverse both go to either quadrant 1 or quadrant 4, then you're in pretty good shape. So here's example 3. Again, find y in each equation. And in part A, it says y equals arctangent of √3. So we know that we're looking for an angle whose tangent is √3, and first we need to decide what quadrant that angle would be in. This is a positive tangent value, so if our choices for quadrants are 1 and 4, then we're going to have to go with quadrant 1 because that's the quadrant that has positive tangent values. Okay, so we're looking for a quadrant 1 angle, and √3 is one of our memorized tangent values. So we know that the reference angle here would be 60 degrees, or in radians we could say that this angle is pi/3 radians. In part B, we're looking for an angle whose tangent value is -1, and that angle has to be in either quadrant 1 or quadrant 4. And since this is a negative tangent value, we know that our angle is going to have to be in quadrant 4, so it's going to be a negative angle. And we know that the reference angle here has to be 45 degrees because we memorized that the tangent of 45 degrees is 1. So if that reference angle is 45 degrees, then this negative angle is -45 degrees, or in radians, -pi/4. Before we move on and talk about the other three inverse functions, let's pause a minute and talk about approximating inverse function values. So your calculator knows the rules for the inverse circular functions. That's great, right? So whenever you use your calculator to get an inverse function value, you'll just need to make sure that your calculator is set in the mode you need. If you need the answer to come back to you in degrees, make sure your calculator is in degree mode. If you need the answer to come back to you in radians, make sure your calculator is set in radian mode. So here's example 4, and we're going to use a calculator to approximate each value. In part A, it says evaluate and state in decimal degrees. So make sure that your calculator is set in degrees. And they're asking us to find the arc cosine of negative 0.13348. So you know that this is just inverse cosine. So you're going to press on your calculator second button, then cosine, and then enter your negative 0.13348. And when you press equal, your calculator should say 97.67 degrees. In part B, it says evaluate and state in radians. And so you'll want to switch your calculator into radians now. And then to find tangent inverse of negative 7.78286, you'll just press second tangent and then negative 7.78286. And when you hit equal there, you should get y equals negative 1.443 radians. Now I rounded here to 2 decimal places on part A and 3 decimal places on part B, but you know that when you're working in MyLab, you always read the instructions under the answer box to see how many decimal places MyLab expects you to keep. Okay, now we're going to talk about inverse secant and inverse cosecant. There's some good news here. The quadrants for secant inverse of x are the same as the quadrants for cosine inverse of x. So you know that secant and cosine are reciprocals of each other, so it makes sense that secant inverse and cosine inverse give answers that are in the same 2 quadrants. We know that cosine inverse is going to give us an angle that's between 0 and pi radians, and therefore secant inverse does the same thing. It will give us an answer in either quadrant 1 or quadrant 2. And the quadrants for cosecant inverse are the same as the quadrants for sine inverse. And so we know that sine inverse has to give us an answer between negative 90 degrees and positive 90 degrees. And therefore cosecant inverse will do the same thing. Cosecant inverse will always give us an answer that's either in quadrant 4 or quadrant 1. Now, as you've seen before, our calculators do not have inverse secant buttons or inverse cosecant buttons. So to evaluate inverse secant and inverse cosecant, here's what we'll do. We will translate out of inverse form, and then we will take the reciprocal on both sides. That will allow us to replace cosecant x with sine of x, or secant of x with cosine of x. And then we can translate back into inverse form because we do have a sine inverse button and a cosine inverse button. And that will allow us to evaluate. Now, you may not have to do this last step because once you get finished with step 2, you may know the answer. If we're working with one of our memorized exact values, you won't even need to do step 3. Really, step 3 is only necessary if you're using the calculator. So let's try it out. Here's example 5, and it says find the degree measure of theta in the following. In part A, it says theta equals the cosecant inverse of 2 square root of 3 over 3. Okay, well, we can't put this in our calculator because we don't have an inverse cosecant button on our calculator. So let's translate out of inverse form. We know that if theta is equal to cosecant inverse of this number, that means that cosecant of theta is equal to this number, 2 square root of 3 over 3. See, that's what I mean when I say translate out of inverse form. And all that does is it swaps the input and the output. Now we're ready to do the reciprocal of both sides. So the reciprocal of cosecant theta is sine of theta. And I need to do the reciprocal of this number, but I notice that this value has been rationalized. So I just want to remember that before this was rationalized, it would have said 2 over square root of 3. And this is the number I want to do the reciprocal of. So the reciprocal of the cosecant of theta is sine of theta. And the reciprocal of 2 over square root of 3 is square root of 3 over 2. Now, if you forget to think about the unrationalized number, that's okay. If you do the reciprocal of this rationalized number, that's fine. It's not wrong. It's just that then you'll have to rationalize it and simplify. So it's just an extra couple of steps. But now we know that the sine of theta is square root of 3 over 2. At this point, if you want the calculator to evaluate it for you, you can switch back into inverse form. But this happens to be one of our memorized sine values. So we know that this goes with a reference angle of 60 degrees. And we also know that because this is a positive sine value, the answer has to be a quadrant 1 angle. And so if the sine of theta is square root of 3 over 2, that must mean that theta is 60 degrees. In part B, we have theta equals secant inverse of negative 3.52. So to evaluate this, the first thing to do is translate out of inverse form. So if theta is secant inverse of this number, that means the secant of theta is that number, is negative 3.52. Now we can translate from secant to cosine. So if the secant of theta is negative 3.52, then the reciprocal of secant is cosine, and the reciprocal of this number is 1 over negative 3.52. Now this is not one of our memorized values, so in this case we will have to translate back into inverse form to find theta. So now we say if the cosine of theta is this number, then that means that cosine inverse of this number is theta. Now the calculator is going to give us an answer here, and we know that it's going to be a quadrant 2 angle, because if the only two quadrants that our answer can be in are quadrant 1 and quadrant 2, then we know that a negative cosine value is going to have to match up with a quadrant 2 angle. And sure enough, when you enter this in the calculator, you get theta equals 106.5 degrees. Now we're ready to talk about inverse cotangent. And there is a little special twist that you'll have to remember when you think about inverse cotangent. So look at this table that I've copied out of the textbook for us. When we're looking at the inverse sine function, we know that the angle that we will get is either going to be a quadrant 1 or quadrant 4 angle. And same thing for inverse cosecant. It's either quadrant 1 or quadrant 4. For inverse cosine, the answer will either be in quadrant 1 or quadrant 2. And same thing for inverse secant. The angle will either be in quadrant 1 or quadrant 2. So when we think about inverse tangent, we know that the answer has to be in either quadrant 1 or quadrant 4. We would expect inverse cotangent to do the same thing, but it does not. And there's a reason for that, and it has to do with the way the graphs of these functions work. Now I know that in this course we have not looked at the graphs of tangent or cotangent, so you'll just have to take my word for it. But because of the way that the graph of cotangent works, it makes more sense for cotangent inverse of x to have a range from 0 to pi rather than negative pi over 2 to positive pi over 2 like tangent inverse. So what does all this mean for us? Well, just like we used the inverse sine button on the calculator to evaluate inverse cosecant, we will be using the inverse tangent button on the calculator to evaluate inverse cotangent. Now, since the inverse cotangent of a positive number is a quadrant 1 angle, and the tangent inverse button on the calculator will give us a quadrant 1 angle, there's no adjustment necessary to find the inverse cotangent of a positive number. But if we use the inverse tangent button to evaluate the inverse cotangent of a negative number, then the calculator will return a quadrant 4 angle. But because we're trying to evaluate inverse cotangent, we should get a quadrant 2 angle. So the bottom line is that if you need to find the inverse cotangent of a negative number, then you'll need to add pi radians to your answer if you're working in radians, or 180 degrees if you're working in degrees, to move the angle from quadrant 4 to quadrant 2. Now let's see how we have to adjust our steps to take this into account. So here are the steps for finding inverse cotangent, and these are the same steps that we use to find inverse secant and inverse cosecant, except we have the added step of changing a quadrant 4 answer to a quadrant 2 answer. So again, we will translate out of inverse form. We will take the reciprocal on both sides to change cotangent to tangent. And then we will change back to inverse form if we're using the calculator and evaluate. If we get a negative angle, which will be a quadrant 4 angle, we know that we need to change that to a quadrant 2 angle. So we will either add pi radians or 180 degrees so that we have a quadrant 2 angle. Let's practice. Here's example 6. Use a calculator to give each value. In part A, find y in radians if y equals cotangent inverse of 1.57. Now this is a positive cotangent value, so I need a quadrant 1 answer. And you're going to see in a minute that the calculator will give us a quadrant 1 answer. But first we have to translate out of this inverse form. So if y equals cotangent inverse of this number, that means that the cotangent of y is equal to that number. Swap the input and the output. Now we can go to a reciprocal form. Take the reciprocal of cotangent y, and that's going to be tangent y. Take the reciprocal of 1.57, and that's going to be 1 over 1.57. Now go back to inverse form. So the tangent inverse of this number is going to be y. And when you put this in your calculator, just like it looks here, make sure that your calculator is set in radian mode so you get your answer in radians, and you should get y is approximately 0.567. Now that's a positive answer, and so we know it's a quadrant 1 angle. We're fine. Now let's go to part B, and this says find theta in degrees if theta equals arc cotangent of negative 1.525. So first of all, before we do anything, please go ahead and set your calculator in degrees so we don't forget to do that later. Okay, now arc cotangent is essentially cotangent inverse. So we will be changing from inverse form to regular cotangent form. So if theta is equal to cotangent inverse of this number, that means that the cotangent of theta is equal to that number. Now let's switch into tangent form. So if the cotangent of theta is this number, then taking the reciprocal of both sides, that means that the tangent of theta is the reciprocal of that number. So negative 1 over 1.525. Now you'll notice that I left the negative in the top of the fraction, and it does not matter one bit if you put the negative in the top or the bottom. It doesn't matter here. But now to get an answer from the calculator, we're going to go back to inverse form. So it's going to be tangent inverse of this number equals theta. Now you know that when we do the inverse tangent of a negative number, we're going to get a quadrant 4 answer. But this question initially asked us about inverse cotangent. So we need to give a quadrant 2 answer here. Now let's put this in the calculator just like it is. So inverse tangent of negative 1 over 1.525 gives us theta equals negative 33.25 degrees. Now we know that this is a quadrant 4 answer, but we also know that inverse cotangent is supposed to have either a quadrant 1 or quadrant 2 answer. So the way to change this angle from quadrant 4 to quadrant 2 is to add 180 degrees to it, and that will give us 146.75 degrees. And now that we have worked with all 6 inverse circular functions, let's go ahead and look at example 7. And this one says, find the exact value of each expression without using a calculator. I know that to a lot of students, these problems look a little intimidating. Here in part A, it says, find the sine of the tangent inverse of 3 over 2. And at first, when you look at that, it does look difficult and complicated. But the truth is that you have been working very similar problems to this since nearly the beginning of the course. Remember that tangent inverse is going to give us an answer that is an angle. So this is really saying find the sine of an angle whose tangent is 3 over 2. And because of what we know about tangent inverse, we know that that angle will either have to be in quadrant 1 or quadrant 4. And because this tangent value is positive, we now know that the quadrant will have to be quadrant 1. So it says find the sine of an angle whose tangent is 3 over 2 and the angle is in quadrant 1. And I'm sure that all of you are familiar with this type of problem. We've seen it over and over again. So what we want to do is draw ourselves an angle that's in quadrant 1, close up the triangle, and then label our sides. If this is a tangent value, then this is y over x. So the vertical side is 3 and the horizontal side is 2. And we know that we can use the Pythagorean theorem to find the hypotenuse. So if these are both legs, we need to add the squares together. So 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. And so this hypotenuse is square root of 13. And so now, whatever this angle is, the sine of this angle will be 3 over square root of 13, y over r. Now this is the sine value, but it does need to have the denominator rationalized. So we'll multiply top and bottom by square root of 13, and that will give us 3 square root of 13 over 13. And now let's look at part B together. It says find the tangent of an angle whose cosine is negative 5 over 13. And we know that inverse cosine has to give us an answer that's either in quadrant 1 or quadrant 2. And because this cosine value is negative, now we're limited to quadrant 2. So we want to find the tangent of an angle whose cosine is negative 5 over 13, and the angle is in quadrant 2. Let's draw ourselves a quadrant 2 angle, close up the triangle here, and then if this is a cosine value, then we have x over r. So let's label our horizontal side with 5 and our hypotenuse with 13. And now to find the vertical side, we subtract the squares. So 13 squared is 169, 5 squared is 25, 169 minus 25 would be 144. And so the vertical side here would be square root of 144, which of course is 12. So now the tangent of this angle, whatever it is in quadrant 2, is going to be negative, because tangent values are negative in quadrant 2, 12 over 5, because the definition of tangent is y over x. So it turns out that example 7 is that very familiar problem where they give us one trig function value and ask us to find another trig function value. But the twist is that every time we've seen this type of problem before, they have told us what quadrant the angle was in. Here, they did not tell us what quadrant the angle was in, but we were able to use what we know about inverse functions to figure out what quadrant that angle had to be in. And so that's the way to approach this type of problem. Okay, that is it for section 6.1. Now that we have finished inverse functions, we can go on in section 6.2 to learn how to solve equations that involve trig functions. So I'll see you next time. Bye-bye.